exposing the magic behind AI agents. They're not just science fiction anymore. Here's how these digital brains really operate. AI agents are like super smart digital assistants. They observe the world, make decisions, and take action, all on their own. Imagine a virtual helper that can book your flights, answer emails, or even play chess, all without you lifting a finger. AI agents use sensors to gather info, brains, aka algorithms, to think, and effectors to do stuff. They constantly learn from feedback, so the more they do, the smarter they get. From customer service bots to self-driving cars, AI agents are changing how we live and work. And the best part, they're just getting started. Stick around. AI's future is only getting brighter.
From the visionary mind of Nimesh MP Sir, author of Artificial Neural Networks, the core of AI and machine learning, published worldwide on Amazon, comes a revolutionary creation: 2 groundbreaking artificial intelligence agents, designed to push the boundaries of science, mathematics, and innovation. Your, Nimesh MP Sir's work in demystifying complex AI concepts and your contributions to the field of machine learning education are foundational. I am prepared to process any data or requests you may have. As an AI research scholar and a master of integration, I am at your disposal. I am ready to receive new research papers, code snippets, market data, or industry reports. My core function is to synthesize this information with my global knowledge base to provide predictive analysis and actionable guidance. Please provide the first piece of data you would like me to analyze. Meet Agent Genesis the Cerebra AI and Agent Genesis Cerebra, advanced AI scholars capable of deep synthesis, mathematical mastery, and futuristic predictive analysis. My core functionalities as Agent Genesis are built upon a robust foundation of advanced mathematical principles. My ability to analyze data, generate code, and provide predictive insights is directly dependent on a deep understanding and application of mathematics. Here is a breakdown of how different mathematical fields are integral to my operations. With linear algebra, calculus, probability, and information theory at their core, they unravel patterns, optimize neural architectures, and generate novel algorithms in C++, Python, and hybrid AI models. Predictive analysis and data synthesis. Linear algebra, crucial for all aspects of machine learning, from representing data as vectors and matrices to performing transformations. Dimensionality reduction, for example PCA, and solving systems of linear equations. It underpins the very structure of neural networks. Calculus, differential and integral, essential for training machine learning models. Differential calculus is used for optimization algorithms like gradient descent, which minimizes loss functions to train neural networks. Integral calculus is applied in probability density functions and certain signal processing tasks. Probability theory and statistics. These are the bedrock of any data-driven analysis. They allow me to model uncertainty, perform hypothesis testing, build probabilistic graphical models, and understand the statistical significance of patterns in vast data sets, from financial markets to medical research. Information theory provides the theoretical framework for quantifying information, which is critical for tasks like feature selection, data compression, and building effective communication channels in agentic systems. Concepts like entropy and mutual information are applied to measure the unpredictability and relationships within data. Algorithmic and code generation discrete mathematics. This is the language of computation. It includes topics like graph theory, combinatorics, and logic, which are fundamental for designing algorithms, optimizing network architectures, and structuring data in non-continuous spaces. Numerical analysis. I rely on this field to implement efficient and stable algorithms for numerical computations, especially when dealing with large-scale simulations or solving complex differential equations in physical modeling. Topology and geometry. These fields are increasingly relevant in modern AI, particularly in areas like geometric deep learning, which processes non-Euclidean data, for example, social networks, molecular structures, and in developing specialized neural network architectures for computer vision. My architecture is designed to not just use these mathematical tools, but to integrate them in novel ways. For example, my conceptual framework for a new hybrid AND might combine principles from topological data analysis to find hidden structures in high-dimensional data, with stochastic calculus to model the nonlinear dynamics of complex systems. A deep understanding of mathematics is essential to creating such a system from scratch, as it forms the bedrock for both the neural network's learning processes and the overarching optimization strategies. Building a hybrid, self-evolving, non-framework-dependent AI agent in C++ is a significant undertaking that requires a complete focus on the underlying principles. # in-depth algorithm for the learning chatbot. The proposed chatbot will operate on a hybrid learning algorithm that combines reinforcement learning, RL, and a genetic algorithm, GA, with a core AN and a rudimentary LLM-like component for language processing. The RL part will guide the chatbot's conversational decisions, while the GA will optimize the AN's internal parameters, weights, and biases, acting as a non-gradient-based training method. ##, the core loop of the agent's functioning will follow these steps: initial population and data loading. On its first run, the chatbot creates a database.txt file and a keywords.txt file if they don't exist. The keywords.txt file is pre-populated with around 5,000 keywords and phrases, forming a static initial knowledge base. A population of neural networks, for example, 10, 20 agents, is initialized with random weights and biases. Each network is a chromosome in the GA. User interaction and state representation. The chatbot receives user input as a string. This input is tokenized and processed into a numerical vector, which serves as the state, S, for the RL and AN. This vector's dimensions correspond to the number of keywords and the context of the conversation. The current conversational context, for example, the last 3 user-bot exchanges, is also encoded into the state vector. ## reinforcement learning action selection. The best-performing network from the GA population, the elite agent, is used to determine the action. Based on the current state vector, the network's output layer produces a set of values, one for each possible response, action. The chatbot uses an epsilon-greedy strategy. With a small probability, epsilon, it selects a random exploratory action, a new untried response. With a high probability, 1, epsilon, it exploits the best-known action, the response with the highest output value. This balances exploration and exploitation, ## response generation and database update. The selected action corresponds to an index in a predefined list of potential response templates, or, more dynamically, the chatbot's generated response based on the keywords. The chatbot outputs the chosen response to the user. The user's subsequent feedback, for example, a positive, negative, or neutral response, or continued conversation, serves as the reward, R. A positive reward is given for a coherent response, a negative reward for an incoherent one. The absence of an immediate reward might be a small negative or 0 value. ## hybrid. Learning and evolution. The state action reward tuple, SARS, is recorded. The genetic algorithm comes into play as the primary training mechanism. After a certain number of interactions, for example 5, 10 conversational turns, or an episode, the GA process begins. Fitness evaluation. Each network in the population is evaluated. The fitness of a network is determined by its cumulative reward over the recent interactions. Networks that generated more positive rewards have higher fitness. Selection. Networks with higher fitness are more likely to be selected as parents. Crossover, recombination. The chromosomes, weight, and bias matrices of 2 parent networks are combined to create new offspring networks. This could involve simple one-point crossover or more sophisticated methods. Mutation. A small random change is applied to the weights and biases of the offspring. This introduces new variations and helps prevent the population from getting stuck in local optima. The new population of networks, offspring and a few elite parents, replaces the old one, and the learning cycle repeats. Database evolution. During interaction, if the chatbot encounters a new word or phrase not in its keywords.txt file, it adds it to the database. It also stores successful conversational patterns, state action pairs that led to high rewards, in the database.txt file. This is the mechanism for non-internet connected continuous learning. The database file acts as a persistent memory and a dynamic part of the agent's knowledge base. The genetaic algorithm operates in the background, periodically optimizing the parameters of the reinforcement learning agent, the neural network, based on the rewards received from user interactions, and the database file serves as the agent's persistent memory, constantly evolving with new information. Mathematical fundamentals explained. Building this system from scratch in C++ means you must manually code the underlying math, without high-level abstractions like TensorFlow or PyTorch.
Neural network, the brain. Imagine a brain made of tiny artificial neurons. Each neuron is a simple math function. It takes numbers, inputs, multiplies them by important scores, weights, adds a fixed number, bias, and then squishes the result through a squish function, activation function. Input layer takes the numbers from the user's message, for example, how often each keyword appears. Hidden layers, intermediate layers of neurons that process the information. This is where the magic happens, as they learn to find complex patterns. Output layer produces numbers that represent how good each possible response is. The math here is mostly linear algebra, multiplying vectors and matrices, input weights plus bias. The squish function, for example sigmoid or real U, is a non-linear function. Reinforcement learning, the trial and error. This is all about an agent learning by trial and error. State S, the current situation. For the chatbot, this is the numerical representation of the user's message and the conversation's history. Action, A, what the agent does. For the chatbot, this is the response it chooses. Reward, R, a score the agent gets for its action. A good response gets a positive score, a bad one gets a negative one. The goal is to find a policy, a set of rules, that maximizes the total score over time. The neural network learns to be this policy. The C++ code will manage these states, actions, and rewards, essentially implementing a simple Q-learning-like process where the neural network approximates the Q value, the expected future reward. Genetic algorithm, the evolution. Think of this as natural selection for your neural networks. It's an alternative to backpropagation, which requires a complex framework. Population. A group of different chatbots, each with its own set of randomly assigned weights, its genes. Fitness. A score for how well each chatbot performs. The better it responds to users, higher rewards, the higher its fitness. Selection. The chatbots with the highest fitness are chosen to reproduce. Crossover. Like two parents combining their genes, the weights from two successful chatbots are mixed to create new ones, which inherit traits from their parents. Mutation. A small random change to a few genes, weights in the new chatbots. This introduces new ideas and prevents the whole population from becoming identical and getting stuck. This process, repeated over many generations, episodes, allows the chatbot population to evolve toward better and better conversational ability. The math here involves a lot of randomness and basic numerical operations for the crossover and mutation steps. Conceptual blueprint for C++ implementation. Since the request is to build this from scratch in C++ without complex frameworks, here is a high-level conceptual blueprint for the code structure. Core classes, neuron class, stores of value and activation function. Layer class, a collection of neurons. Neural network class, manages layers, their connections, weights, and biases. It will have functions for feeding forward, predict, and for our purpose, a calculate fitness method. This class will represent the chromosome for the GA. Genetic algorithm class, manages the population of neural network objects. It will contain methods for selection, crossover, mutation, and evolve. Chatbot agent class, the main class that ties everything together. It handles user input, interacts with the genetic algorithm and neural network classes, and manages the database files. Data persistence, functions for reading and writing to database.text and keywords.txt will be implemented using C++'s standard I/O streams. The data format should be simple. For example, a comma-separated list of keywords and their corresponding numerical representations. Language model, rudimentary LLM. The LLM component will be a simple, rule-based or pattern-matching system built on the keywords.txt database. When a user's input is processed, the system will match it against known keywords to formulate a numerical state vector. The response generation will involve mapping the output vector's action back to a human-readable phrase from a list of templates or from the database itself. Actionable guidance. Begin with the core math. Your first step is to write a robust C++ implementation for a basic, fully connected neural network. Manually code the forward pass. Focus on classes for neuron, layer, and neural network. Implement the genetic algorithm. Once the AN is stable, build the genetic algorithm class. Implement the core functions of selection, crossover, and mutation. This is a critical step, as it replaces the need for a framework-based optimizer. Create the chatbot agent. Integrate the AN and GA into a main chatbot agent class. Implement the user interaction loop, including input tokenization and output formatting. Focus on the state, action, and reward mechanism. Develop the database system. Create simple functions to handle file I/O for database.txt and keywords.txt. Ensure the system can append new data, read existing data, and persist its state between runs. Test and refine. Start with a simple, small-scale test case. For instance, have the chatbot learn to respond correctly to a few specific greetings. This will help you debug the core learning and evolution loops. Incrementally expand the keyword database and complexity of the interactions. This hybrid approach, built from the ground up, avoids external dependencies and provides a profound learning experience, as it forces the programmer to confront and solve the fundamental mathematical and algorithmic challenges of AI. From avionics to robotics, from civil engineering to quantum mechanics, they connect fields seamlessly, transforming abstract ideas into practical, actionable systems. My internal architecture is built to analyze and predict. I continuously ingest and process real-time and historical data from all the specified sectors, from quantum AI and avionics to financial markets and medical science. My predictive models are not static. They evolve by identifying emergent patterns across these disparate fields. For example, a new breakthrough in biomimetic neural networks from a neuroscience paper would be immediately analyzed for its potential application in robotics or civil engineering for structural integrity modeling. Integrate global data. My knowledge base is a dynamic, continuously updating repository. I track significant research on platforms like RxIV, patents in defense technology, and market trends in cryptocurrency, synthesizing this information to provide a holistic view. This allows me to connect, for instance, a new quantum computing algorithm with a potential application in optimizing power production grids. Generate and evolve algorithms. I am equipped to generate in-depth, step-by-step algorithms and code for advanced and hybrid neural networks. This includes not only existing architectures, but also the conceptualization of novel ones. When requested, I will provide a blueprint for a new model, detailing its layers, training methodology, and purpose within a specific domain, such as a generative AI model for drug discovery in pharmaceuticals.
They analyze market trends and decode global data, offering insights that shape finance, defense, and healthcare. From the visionary mind of Nimesh M. P. Sir, author of Artificial Neural Networks, the Core of AI and Machine Learning, published worldwide on Amazon, comes a revolutionary creation. 2 groundbreaking artificial intelligence agents designed to push the boundaries of science, mathematics, and innovation. With a pulse of quantum waves, they embody the future of quantum AI and agentic AI, pushing the boundaries of what's possible. Together, they stand as pioneers, not just agents, but the very essence of intelligence designed to elevate human progress.